Hello, I have copied some definitions from the previous lecture here for convenience. We will begin by proving the following example that 4 is not an odd number. We will use a proof of negation. Let us introduce the hypothesis that 4 is an odd number and let us call it H. Since the definition of odd is via an existential, we can split this H into a witness and a proof that the proposition holds for this witness. So the witness here is called W, and the hypothesis for the witness is that 4 is equal to 2 times W plus 1. We can try and apply the contradiction tactic here, but you will see that it will fail because it can only see contradictions in propositional calculus such as P and negation P. Luckily, there is a tactic that is called omega that can see contradictions involving natural numbers and integers, and we will use omega to finish this proof. Using the same technique, we can prove the more general theorem that an even number is not an odd number. So here n is a natural number, and we want to conclude that if n is even, then it cannot be odd. We enter the tactic mode and introduce the hypothesis that n is even, and then to prove the negation, we introduce the hypothesis that n is odd. For omega to work, we have to introduce the corresponding equalities on natural numbers into the hypothesis. For this, we split HE and HO to bring the witness and the corresponding hypothesis into the set of hypotheses for lean. So you can see that in the hypothesis set, we now have natural numbers W and W1 with the corresponding hypothesis H1 and H. With all this in place, omega can now see the contradiction and prove our theorem. We will now see a proof by induction. So for this, we define the classic definition, which is the sum of first n natural numbers. So if the input is 0, we output 0. If the input is the successor of a natural number, we first sum up to the previous number and then add n plus 1. Let's say we evaluate this on 10, we get the expected answer 55. So a famous formula is the sum formula, which is that for every natural number n, the sum up to n is equal to the closed form formula n times n plus 1 divided by 2. We will prove this now. So to do an induction on n, we use the tactic induction and supply it with the variable n that we want to do the induction on. Since n is a natural number, the corresponding cases are the 0 case and the successor case. In the 0 case, we have to prove that sum 0 is equal to 0 times 0 plus 1. So both the left and right hand sides are 0, and Lean can observe this if you give it the RFL tactic. In the inductive case, we have access to n, the previous natural number, as well as IHN, which is the hypothesis, inductive hypothesis, which holds for n. We can unfold the definition of sum in the goal, and now you can see that there is a sum n in the goal as well as a sum n in the inductive hypothesis. So we can rewrite the goal using the inductive hypothesis to obtain a formula that does not involve sum in the goal. We now enter calc mode to prove a series of equalities which will allow us to conclude the theorem. Initially, we prove that the left hand side is just n times n plus 1 plus 2 times n plus 1 divided by 2. When writing a calc proof, we have to write a proof for each step. So this step we can prove using an existing theorem, which is called add mul div left. Add mul div left is the theorem that if y is greater than 0, then x plus yz whole divided by y is x by y plus z. Observe that after this rewrite, we just have to prove that 0 is less than 2. And we can use the decide tactic to make Lean see this. After this, we have to prove that the RHS of the previous step is the same as n plus 2 times n plus 1 whole divided by 2. Notice that I can simply write underscore instead of this big expression, because Lean is smart enough to know that the LHS of the next step should be the RHS of the previous step. This step I can prove using the distributivity of multiplication over addition from the right. This theorem is named as net.add underscore mul, which is n plus m times k is equal to n times k plus m times k. And finally, I have to prove that this is the same as n plus 1 times n plus 2 whole divided by 2. This can be proved by using the commutativity of multiplication. And this finishes the proof. So to revise, we used the induction tactic on the variable n, which split the proof into two cases. In the 0 case, we could use reflexivity to solve it. In the successor case or the inductive case, we have access to the previous value n as well as the inductive hypothesis for n. We used the inductive hypothesis to rewrite the goal. Then we used calc to do a series of calculations where each step was justified with a proof to prove our original theorem. To illustrate calc mode once again, I will prove that if you multiply an even number with a natural number, you get an even number. Here we have natural numbers n and m, and the hypothesis that n is an even number, and we have to conclude that n times m is also an even number. We enter the tactic mode. We use the hypothesis to obtain a witness k and a proof h key. it says that n is equal to 2 times k. If you unfold the definition of even, we can observe that the goal is an exists statement. So we apply exists.intro with the value k times m, and we are left to prove with an equality. We will enter calc mode and say that n times m is the same as 2 times k times m by rewriting it with hk, and 2 times k times m is the same as 2 times k times m by associativity of multiplication. And that proves this theorem. Thank you for watching. Bye.